So, students, welcome to video class 16, and this is the last part or the last session of the time domain analysis of a second order system subjected to a unit step response. And in the last session, we have concluded that the time response due to or the step response of a second order system, and this is we concluded by a comparison of the step response of second order system for various values of zeta. So these figures are actually showing the response for different zeta values, right? Now you have a zeta between 0 and 1, and zeta equal to 1, and zeta greater than 1. So between 0 and 1, we can see there is some amount of oscillation, but there is damping. It's not growing. So because of the presence of a positive zeta will always make the system either damped or critically damped or over damped. So as long as the zeta remains between 0 and 1, that is called as an under damped. Any oscillations will be uh, will uh, will be nullified after a period of time. Now at zeta equal to 1, it's critically damped as shown in this green line. This is just missing that oscillation, and this is a condition where zeta is greater than 1. That's called as over damped condition. Okay, so this is the comparison of the step response of a second order system uh, based on different values of zeta. And zeta, mind you that zeta is the damping ratio, or it is the zeta which actually determines how much amount of damping is required so as to nullify if any oscillations are there in output. Okay, now in this session what we will be starting with something called as a transient response specification. Transient response specification of a second order system based on the step response of a second order system with zeta between 0 and 1. That means we will be considering an underdamped system, and based on and we'll be studying some of the transient response specifications. Okay, I'll explain what is this transient response specifications and all that. So that's what we are going to study in this session. Okay, now to study the transient response specifications, so I'll be starting with considering an underdamped second order system as we have studied. Now, what is the meaning of underdamped system? An underdamped system is a system whose response looks like this, and the zeta lies in between 0 and 1. So we'll have some oscillations there, and we see that the oscillation subsequently dies off, or it reduces almost to 0. That means almost oscillation gets vanished after some period of time. So that's why. So that means when you look at this is an example of a zeta which lies in between 0 and 1, and this condition we call as a underdamped condition. Now this is the time axis. Now look at this. Now why we selected this underdamped condition? Because in the underdamped condition we'll be able to study the different variations of the output till it reaches the desired value. Okay, now this is actually your desired value as far as a step input given to a control system. As far as a control system is concerned, the output must be maintained at 1. If you are giving step input, means you are giving set input, step input as the set input. So that means the set input is the input which you are desiring the output to be. So output must be equal to 1. But when you look at this in an underdamped system, we can't see that initially itself it is reaching 1. It's gradually, there is some amount of oscillation, and finally it reaches a value almost equal to 1. So say okay, now let us consider, suppose the error between these two. That is, at this point, say if you evaluated the error, say let it be 2% error. Okay, let it be 2%. Okay, now now up to this point, if we are not now if we are providing a 2% tolerance, that is, we are not at all worried about that error, then we can assume that after this point, say there is a time has to be taken for this, and for the meantime I'm just calling it as TS. We'll come to that later. So till this time the output varies, right, continuously, that is in an oscillating mode, and finally it reaches almost equal to 1, or we just assume that there is only a 2% error after this. That means after this time TS, the system almost achieves the desired value, and the part of that response where it reaches this desired value is called as the steady steady state response. Okay, so this is actually the output response of a control system, of a second order system, right, which is subjected to a unit step input. So we have seen that this value, the desired value, the time after which the response reaches the steady state, we call as a steady state response. Now, the time till it reaches the steady state, or over this time period, over this time, okay, we can call this response, this part of the response, as what? As the transient response. As the transient response. Now, why transient? It is transiting, or it is changing from the zero inputs, from the zero response to 1. So there is a transition. It will take, a practical system will take some amount of time to reach the steady state. Now the response before this steady state response is what is called as a steady state, is called as the transient response of that system. Okay, now we can define various time. So based on the time axis, okay, or based on this response, we can we can study some of the specifications based on the graph. Okay, we'll be defining some time as well as some parameters of the second order system from this response. Okay, now the first thing that we can see is this output response. It reaches, at first it reaches the 100% of output at this time. It's not at this time it reaches 1. It reaches, first time it reaches it passes through 1 is, so we can define that point as by a particular time. Let us call that as TR. Okay, now look at this point. What is the specialty of this point? The output goes to a magnitude, and this is the maximum magnitude that the output can have. Now after this you can see that this output reduces, and it is not at all coming to this level, right? So you can call that also by another time, and I'm denoting that as TP, right? And this I have already explained, that the time it took to reach the steady state response. Okay, now this TR is what is called as the rise time. TP is called as the peak time, while Ts is called as a settling time. Okay, so these are very important times with regard to a transient response. These are very important specifications of an underdamped second order system. So if it is an underdamped system, that system will be having three things, that is rise time TR. So it can be, the response can be specified by TR, TP and TS. Okay, so now these specifications are very important in the design of a such system. So that's why we are studying this transient response specifications. Okay, now let's start to define each. Now, the first of all, let us see what is this rise time. It is actually defined as the time taken or needed, time needed for the response to reach, for the response to reach what? Reach 100%, that is 0 to 100% of the desired value, or it is also defined as the time taken for the needed for the response to reach from 0 to 90% of the desired value. Okay, now these are the definitions for two different systems. Now 0 to 100% of desired value is defined when the system is an underdamped system, while 0 to 90% will be, this definition is the definition for an overdamped system. Okay, that is the rise time of an overdamped system is defined as the time needed for the response to reach from 0 to reach 90% from 0, right? From 0 to 90%. So that's the rise time. Now, this is a case of an underdamped system. So here we will be using this definition, 0 to 100%. Look at this. The time response, as the time increases, the C of t increases, and it's reaching, the first time it reaches the desired value, which is equal to 1, and the time the system needed to reach this 1 is what is called as a rise time. And since it is an underdamped system, we take the definition to be 100%. Now, why for an overdamped system we are considering this definition? Because look at this. So this is an example of an okay, we have already seen that this is a graph, the graph which shows theta greater than 1, right? Now look at this, there is no oscillation, and practically speaking, this system is not going to achieve its steady state, right? Now it goes, now it won't be, the graph shows that it's not touching the 1. So you cannot define the rise time to be equal to 100% because it's not reaching the 100% at any real time, right? So because of the fact that we define an overdamped system as a time needed for the system to reach the 90% from 0, and that's for the overdamped system. Now, since we are considering only underdamped second order system, we are defining the rise time, or we are going to find out this TR. Then this TR is defined as the time needed for the response to reach 100% from 0 of the desired value. Okay, is it clear? Okay, now our next aim is to get an expression for this rise time based on the second order time domain response, right? So we have already seen in our study that the C of t is given by 1 minus e raised to minus eta omega n into t, 1 minus eta square sine omega dt plus phi. So how will you use this equation to evaluate CTR? TR. Now we know that TR is the time taken by the system, so that C of t becomes equal to 1, right? C of t becomes equal to 1. That means if you can equate C of t to be equal to 1, then you can find an expression for t, right? If you can call this C of t. So what is TR? TR is a time needed by the system response where C of t becomes equal to 1. So if you put 1 here, you can evaluate the corresponding time is what is called as TR, right? Because it is at this time the system reaches the 100% at first. Okay, so that what I do is I'm considering this expression, I'm equating this to equal to 1. So C of t, so what is this TR? TR is the time where C of t becomes equal to 1. I'm simply substituting equal to C of t to be 1. 1 is equated to this, and equating that. Okay, now when you look at this, so you will be getting it as 1 is equal to 1 minus e raised to minus eta omega n t root of 1 minus eta square sine omega n into root of 1 minus eta square t plus phi. Hope you understood why I put 1. So I'm considering this as the first instant. The first instant the output reaches there. Now when you go through this, you can see that this output again passes through this 1 again many times. So this is the first instant where the output reaches this 1, right? So that time is what is called as a rise time. So you can say in an underdamped system, it is the first instant at which the output reaches the 100% for an underdamped system. Okay, that also you can specify when you say the rise time definition. Okay, now equating this 1 is equal to this. So what you can say is, okay, this 1 and 1 get cancelled. This 1 and 1 get cancelled, meaning e raised to minus theta omega nt divided by root of 1 minus theta square sine omega n into root of 1 minus theta square t. Now what you can call this t? Now this t can be replaced as tr because this is rise time. If you are equating this c of t to 1, meaning that is how the rise time is defined. This is the time needed by the system response to reach 1. So that means obviously this t becomes tr, right? This becomes tr, or this tr, this is tr. Now, what is this? This 1 and 1 get cancelled. That means this quantity becomes equal to 0, right? Now, this cannot be equal to 0 because this is an exponential signal. As long as there is some amount of time, anyway, this TR will be a quantity, a positive quantity. As long as there is a quantity for this, this cannot be equal to 0. So, the only chance is sine omega n into root of 1 minus theta square into TR, that is a plus phi, right? Plus phi, right? Plus phi is equal to 0, right? Plus phi is equal to 0. So sine omega n into root of 1 minus theta square TR plus phi is equal to 0. Or this is a trigonometric equation, and the solution to this equation is the solution to call this as 1. Solution to 1 is what? Solution to 1 is, when you have this sine theta is equal to 0, then we will say that theta is equal to n pi, right? Theta is equal to n pi, right? So that means you can say that omega n into root of 1 minus theta square into tr plus phi, that is theta. This theta is equal to n pi. Now, I told you that this rise time is the time needed for the response to reach 100% of the desired value at the first instant. Okay, at the first instant. So there are a lot of times where the response reaches 1. So we are concerned only about at the first instant. So since it is first instant, we put n to be 1. This shows the first instant. Okay, hope you understood. This is very important. You need it later on in our derivation. We also need this. So your n pi, this n and this n has nothing to do with this. This omega n refers to the natural oscillation. So this n becomes equal to 1. That means omega n into root of 1 minus theta square tr plus phi is equal to pi, right? Or omega n into root of 1 minus theta square into tr is equal to pi minus phi, or what is tr? tr is equal to pi minus phi divided by omega n into root of 1 minus theta square, right? So this is tr. Now, okay, now you can know where what is phi, where phi is actually equal to tan inverse root of 1 minus theta square by theta. Okay, so this is it. So that means this tr, we have seen that this tr, or the rise time, is given by pi minus phi divided by omega n into root of 1 minus theta square, where phi is given by tan inverse root of 1 minus theta square by theta. Okay, hope it is clear. Now this is what is called as the rise time. Now the second specification is peak time, TP, as I have shown in this figure, TP or peak time. Now how will you define this peak time? Now before going into this peak time, you need to have one more term. I'll just define and we'll come to that later in the derivation part. We'll have to see a term called as maximum overshoot. Okay, now maximum overshoot is defined as the maximum positive deviation, maximum positive deviation of the output, not the negative, positive deviation of the output from the desired value, from the desired value. Okay, from the desired value. Now look at this, you must be very careful in this. Is not a time, this is also one of the times, specification, but mind you that this is not time, this deals with the amplitude, right? Now how will you now maximum overshoot is the maximum positive deviation, maximum positive deviation from the desired value. Now that means coming to this, right? Look at this expression. So what is a positive deviation means? The deviation from one in the positive direction. This is called as a negative deviation. This is the positive deviation. This is also positive deviation. This is negative deviation, right? Now from this figure we know that this is the maximum point the output has reached. Now after this time this maximum value reduces, right? Reduces, and it is no longer coming to this point at any of the other times, right? The only time that it reaches the maximum point, and this amplitude or this deviation, okay, this deviation, okay, I'll mark this. This deviation is what is called as maximum overshoot. Okay, so this deviation, I'm marking it with the green ink. This deviation is what is called as a maximum overshoot. Okay, hope you understood. So now, what must be this peak time? So from this, it's very simple. It is the time needed by the second order system to reach the maximum overshoot. Okay, so you can say that maximum. So TP or peak time can be defined as the time needed for the system to reach what? To reach maximum overshoot. Maximum overshoot. Okay, so hope you understood this. So this is the maximum overshoot, and the time the response to reach this maximum overshoot is what is called as the peak time. Now, how will you get this TP by using this expression? Now, this is the maximum value this C of t can have, right? Now, if you look at this graph, C of t is not going higher than this maximum overshoot at any time other than this TP, right? So you can you can find the condition for the C of t to be maximum. How will you find the condition for how will you find the condition for a function to be maximum? And that is nothing but you take the derivative of that function and equate to 0, you will get the condition for the function to be maximum. You have studied in your for the function to be maximum. Okay, so you have studied this in your lower classes. Now you are going to apply the same thing in this time domain function, right? You will be differentiating this function with respect to time and equate to 0. When you differentiate and equate to 0, you can call this t as TP because that is the condition. So from that you will be getting that value of t, and that t is called as your peak time, or we will designate that as TP, T suffix P. Okay, so I'm considering again the expression which we have considered for finding out the expression for TR. That is, you are considering again the response equation. C of t is 1 minus a raised to minus eta omega n into t plus phi. What you need to do is you need to differentiate this d of c of t, dc of t by dt, and equate to 0. Now, when you differentiate this, you will get this expression as, say, this is 0, right? Now, this will be, when you differentiate, so what I'm going to find out is dc of t by dt. Now, these are two time domain functions, so you can have a product rule. Applying product rule, you will get this as minus e raised to minus theta omega n into t divided by root of 1 minus theta square, okay, into omega n into, okay, into, so you are differentiating this. So when you differentiate this, you will get this as cos omega n into root of 1 minus theta square t plus phi, right? This into what is a, and you need to multiply by this product, right? So this will be omega n into root of 1 minus theta square, then minus, then you need to differentiate this. Now when you differentiate this, you will get this as e raised to minus theta omega n into t, right, divided by root of 1 minus theta square, right, into minus theta omega n. You need to differentiate by differentiating this. So minus theta omega n into sine omega n into root of 1 minus theta square t plus phi, right? So this is how you, when you differentiate this, what I am doing is this differentiating, this becomes 0. First of all, I will be differentiating this sign, so sine becomes cos, and internal differentiation will lead to this product omega n into root of 1 minus theta square. Then I will be differentiating the first function. Okay, so this will be the product of that differentiation into that sine function. This value is going to be equal to 0, right? That is dc of t by dt is equal to 0, right? Okay, now not that you have a minus sign here. Okay, this minus and minus becomes plus, so this quantity plus this is equal to 0, bringing this term to the right hand side. This term and this term get cancelled, so the resulting will be omega n into root of 1 minus theta square cos omega n into root of 1 minus theta square t plus phi is equal to zeta omega n sine omega sine the same thing. Okay, now you may just do it by yourself. So okay, you can bring this to the denominator side, so that you will be getting this sine divided by cos, that is tan, right? You are having the same thing, right? Sine theta. So you can bring this cos theta down to this sine theta, so you will be getting this as tan theta is equal to omega n, sorry, okay, you can write this theta as tan of omega n into root of 1 minus theta square t plus phi is equal to omega n into, right, omega n into root of 1 minus theta square, omega n into root of 1 minus theta square divided by omega n into theta. This omega and omega cancelled, so you will be getting omega n into root of 1 minus theta square t is equal to root of 1 minus theta square by theta. Now this phi, we know that phi is actually what? Phi is actually tan inverse of root of 1 minus theta square by theta, right? This we have already defined. Okay, now substituting in this equation, you will get tan omega n root of 1 minus theta square t. Now what is this t? Once when you equate this equal to 0, we are actually going to find out tp, right? This is tp. This is tp. So sine tp. So this is the peak time. Time tp plus tan inverse root of 1 minus theta square by theta is equal to 0, right? Right? This is equal to this is equal to root of 1 minus by theta. Okay, now this is also a trigonometric equation of the form that tan theta plus, say, tan inverse, say, x, tan inverse x is equal to x. Okay, it's tan of theta plus, so theta is omega n into root of n, plus tan inverse x, I'm calling this root of 1 minus theta square by x, which is also equal to x. So this is a trigonometric equation. So if this is the case, then the solution for this, that is the value of theta will be, right, the value of theta will be n pi, right? Value of theta will be n pi. This is the solution for this equation, right? Now using that, you can say that this omega n into omega n into omega n into root of 1 minus theta square tp is equal to, that is, this is equal to n pi. This is equal to n pi, right? So this is equal to n pi, where n can be 0, 1, 2, etc. Okay. Now, here also we are considering the first instant. So TP is actually based on what? Based on the maximum overshoot. So this is the maximum overshoot is the is identified by the instant of occurring. The maximum overshoot is identified by putting n is equal to 1. So mind you, this equation is very important for the maximum case. Now in the maximum case you have a value n. When you put n is equal to 1, that is your maximum overshoot. Okay, so now that is your maximum overshoot. Now what is this called as? This is called as the, if this is called as a maximum overshoot, this deviation in the negative direction is called as a maximum undershoot. Okay, or this is the minimum point. You can call in that way as well, the minimum deviation, right? The minimum deviation or the maximum undershoot. Now how will you evaluate the maximum undershoot using this expression? If you put n is equal to 2, that is your second instant, that will give you the minimum, okay, maximum undershoot. Don't say, be careful that this is maximum undershoot, or maximum undershoot refers to the maximum negative deviation from the desired value. Okay, so from this you can evaluate your TP. Now this TP actually corresponds to n is equal to 1 because TP is defined as the time that it takes to reach the maximum overshoot. So TP is equal to, putting n is equal to pi, this will be pi divided by omega n into root of 1 minus theta square, right? So this is TP. So this is called as the peak time. Okay. Now let's move on to the maximum overshoot. Now maximum overshoot is represented by the letter MP. In the graph you can denote this deviation as MP, M suffix P. Or maximum overshoot can be defined as the maximum positive deviation with respect to the desired value. Okay, so as in this figure, okay, it is self-explanatory. So this is the desired value and this is the maximum positive deviation, and that's called as maximum overshoot. And along with this you may take down the definition of maximum undershoot. It is the maximum negative deviation from the desired value, the maximum negative deviation after the rise time. Okay, so that is called as a maximum undershoot. Okay, now and you must also be careful that when you put n is equal to 1, that refers to maximum overshoot. When n is equal to 2, you will get the maximum undershoot. Do remember these two terms, overshoot and undershoot. Okay, now we want to find out, the next specification is we want to find out MP, right? So the second order system, that is a maximum overshoot. So it is not a time parameter, it is an amplitude parameter. Maximum overshoot is just the deviation. That means the change in C of t. It has nothing to do with this. Yeah, of course it has something to do with TP, but this is not what I'm talking. Is maximum overshoot is not time, it is amplitude. Okay, now how will you evaluate that? Now we have already seen the peak time. What is this peak time and maximum overshoot has relevance, right? Has relation, right? Because peak time is the time needed for the system to reach the maximum overshoot. So how do you find this TP? TP is found out by differentiating this C of t to a maximum value, and we got a condition that TP. Now what is the meaning of this TP? At this TP, the output response reaches what? Maximum overshoot, right? Now in another way, so if you can substitute this TP in this equation, this C of t is your maximum overshoot, am I right? So that means at TP the C of t is going to be the maximum deviation. C of t gives you the maximum overshoot, right? Now, or the maximum value of C of t, right? Now how will you find out maximum overshoot, MP? MP, now I'm going to define this MP before going into that. uh, MP is actually, MP is defined as a deviation. Now how will you define this deviation? This point, this is actually your C of t. This point, let us call this as C of t max. This is the maximum value that this output can reach, and this is the positive deviation. Now this C of t minus 1 will give you what? Will give you the maximum overshoot. So this MP is nothing but it is C of t max minus 1. Now what I'm talking it, how will you find out the C of t max? The C of t max is obtained by putting in this equation the value of TP. Why? Because at this TP the output actually reaches what? Reaches this C of t max, right? And the deviation at that point is what is called as a maximum overshoot. Okay, so if you want to get this, so first of all, in order to find out CP, you need to get this maximum value of C of t. Now we know that at this time this output will be at its maximum. So that means if you C of t at TP is actually your C of t max. Am I right? Okay, now what I'm going to do is I'm using this expression, that is TP, substituting this TP in this equation, right, in the C of t. Okay, substituting that. Okay, so look at this. C of t max is equal to 1 minus e raised to minus eta omega n. Instead of t, I put TP, pi by omega n into root of 1 minus eta square by 1 minus eta square. Here also you have a t. Instead of this t, I have put this pi by omega n into root of 1 minus eta square plus 5. Okay, so this is 1 minus. Okay, you will be getting this expression by root of 1 minus theta square, right? So here also you have a 1 minus root of 1 minus theta square. Now substituting these values, so we know that phi is actually tan inverse of root of 1 minus theta square by theta. Okay, now what is the sine phi? Sine phi is actually root of 1 minus theta square. So you can put this sine phi to be root of 1 minus theta square, and this get cancelled. So you will be getting this as 1 minus e raised to minus theta pi by root of 1 minus theta square into the theta square get cancelled. So you will be getting this as 1 minus of, you have a minus of sine phi, so this sine phi and plus this becomes 1 plus, right? Now this is equal to 1 plus e raised to theta pi by root of 1 minus theta square. Now this is actually your C of t max. Now what is your MP? MP is C of t max minus 1. We are concerned only about the deviation. Now that MP is what is called as a maximum overshoot. So this is when you subtract this 1 from this, you will get this MP to be e raised to minus theta pi divided by root of 1 minus theta square. So that is your maximum overshoot. Now one more point is that from this maximum overshoot you can have a relationship or a graph concerning MP and theta. You can see that this MP depends on the value of theta, right? As a theta increases and decreases, there is a change in this MP. Now, as we can find in this equation, as theta increases, what happens to this expression? 1 minus theta becomes smaller and smaller. That means this becomes a higher quantity. So, e raised to minus a higher quantity means it reduces to 0. So, as theta increases, that's what we see here, right? In the comparison thing which we have done in the previous video, that is, look at this. At theta is equal to 1, the maximum overshoot is high, right? As theta increases, what happens to the maximum overshoot? It reduces. And that you will get from from this equation, right? And drawing the cara, you will get, that is, if you are to plot MP versus theta, right? MP versus theta, what you're going to get is, you're going to get a graph like this, because MP is nothing but, MP is an exponential function, right? E raised to exponential function. So what you're going to get is, at theta is equal to 0, what happens at theta is equal to 0? Theta is equal to 0, this becomes 1. MP is maximum. So maximum overshoot, that is at, this is the point where theta equal to 0. That is, this is theta, so 0th value, right? So this is the theta value, and what happens is it reduces to, this is showing an exponential graph, and as theta becomes equal to 1, what happens at theta equal to 1, this becomes this theta root of 1 minus 1, which is 0, e raised to minus infinity, that reduces to 0. So mp gets reduced to 0. So at this point mp is 0, or this is the theta is equal to 1, right? So this is at theta equal to 1, it reduces to 0. So that's what it is shown here, right? In the comparison graph, look at this, look at the graph of where theta is equal to 1. There is no damping, right? No, I mean, sorry, there is no oscillation, right? There is no oscillation, that means there is no maximum overshoot or undershoot. Okay, the reason is theta has reached 1, and that's been explained by this graph. Okay, so hope you understood this. And finally, let's move on to one more thing that is to be studied, that is the fourth parameter, that is the settling time. Now, settling time, I have numerous times I have explained what is the settling time. Okay, now what is the settling time? Settling time is for an underdamped system, the magnitude of the oscillation. So look at this, this is an underdamped system. The magnitude of the oscillation present in the output decays exponentially, right? Exponentially with the time constant. With the time constant, what is going to be its time constant? Now I told you how to find out the time constant. It is the time that you need to substitute here so that this becomes unity. So we know that this t is equal to 1 by theta omega n, or you can call that as the time constant of the second order system. Now, so that means this decays. So this is what it says. This decays, right? The oscillation decays exponentially with the time constant at a rate of 1 by theta omega n. That's what it says. Now, the time needed can be evaluated based on this capital T, right? Now, we have seen that in our previous discussion of first order system, we have seen that if a designer can provide a 2% tolerance and a 5% tolerance. If you give a 2% tolerance, then that will be the TS will be defined as 5T. If you are giving a 5% tolerance, then TS will be 3 times T. Okay, so in this graph it is showing that there is a 2% tolerance. That means this TS is going to be 5T. What is T? T is 1 by theta omega and 5 by theta omega n. So your settling time, how will you define your settling time? It is the time needed to settle down, right? Time needed by the output response to settle down to the steady state, and as in a practical system it is the 2% of the oscillations settle down the oscillations within a 2% of the desired value, and that is known as the settling time. Then that ts is given by it is not 5t, it is 40, right? 40 and 3t, right? It is 40, right? It is 40. 4 times t, it's not 5t, it's 40. When you put 40, you can see that the output will be almost equal to, say, some 0.98. Okay, 0.98 and something. So when you put ts is equal to 3t, you will be able to get this 1 minus something will be giving you 0.95. Okay, all these things I have explained earlier. So this is on a 2%, on a 2% tolerance, the ts is going to be 40. So you can see that it will be 4 by theta omega, and for 2% tolerance, and for a 5% tolerance, your ts settling time will be 3 by theta omega n. Okay, so hope you understood the concept of this. So far what we studied under this transient response specification is, we started with the rise time. We know what is rise time. Rise time is the time needed for the system to reach the desired value 1, and reach the 100% of the output at the very first instant. So that is the rise time. And peak time, when we started to study peak time, we have also defined something called as a maximum overshoot. It is a deviation, positive deviation from the desired value. The time taken to reach that is called as a peak time, TP. And then we went on to define what is this maximum overshoot. In order to find out maximum overshoot, we need to have the maximum value of the output. So for that, we substitute the value of TP in the in the value of CT. Okay, because at that time it reaches the maximum, so you will get the maximum value. Now from that, if you subtract 1, you will get the deviation, maximum overshoot, and we found out an expression for that. So peak time, this is actually your peak time. Then you have the maximum overshoot, and finally at the for the settling time, this can be 4 by theta omega n or 3 by theta omega n based on the tolerance that is provided. Okay.